there we go. We are now live. Oh, hello. Livia, if you can see/hear me, probably more importantly, hear me, I want to ask if you're willing to join the stream so we could have like some sort of live interaction during the lecture component. That is to say, like, put you on the side of the stream, like the stream is on and you would also be live. Okay. I can neither see nor hear you, so I will check. Oh, hi. If you're good to like join on the stream, give me like a thumbs up. Or all right, great. Now we got a party going. All right. Cool. Well, thanks for coming in today, guys. Today is week 2 of our little mini data science curriculum, and we're going to be spending another week looking at some introductory Python components. Why are we doing this? Well, first and foremost, we're going to be doing all of our data science stuff within a Python environment. So if we don't like have a firm grasp on the basics of Python, then we're going to be a little lost coming down the road. And 2, it's just good to know Python. It's a pretty beginner-friendly sort of language, and the environment's not too unapproachable. So it's good to have some just like basic computer science information stored so that we know it. Okay, great. We're gonna get rolling. So intro to Python. There we go. Starting in a few minutes. We're actually starting now. Module 1, part 2. Let's go. Let's get started. So today, what are we going to be talking about? We're going to be, and maybe some of these things don't mean a whole lot now, but we're going to be talking about tuples, dictionaries, loops, functions, modules, packages, all that exciting stuff. So before we go into it, you might be wondering, based on all the information that we learned last week, like why is what we're doing with a computer science that much more efficient than just like us doing it by hand? I mean, what did we learn last week? We learned like integers and like we can add. Great, that just makes it a really complicated calculator. What else can we do? We can like write strings and like store lists, and it's like, okay, that's great, but like what's the practical use of computers then if that's like really the extent of it? That'd be a fair question to ask. And hopefully this week we get to answer a few of these questions in that we are we're exploring different ways of storing information, different ways for information to interact with each other in ways that we don't like have to explicitly define. So information storage then becomes a lot less of like a personal hassle because we can offload that role onto the computer, onto the program. That's one, right? And 2, with loops and functions, we can automate certain processes. And so that we don't have to like do a million things over and over again. And with modules and packages, it's going to give us a way for us to interact with things that people have already written, and therefore it's making our process of like making tasks a lot faster. So that's the draw of computers and stuff, and we need to learn it in order to like put it into practice. Sure, fair, great. So there's the motivation. Let's move on. What's a tuple? Good question. Tuples are a data type, and they're similar to lists in that, oh, by the way, when I change screen, like, does that show up on, I don't want that to be jarring, but anyway, tuples are a data type, and they're similar to lists in that they store information in like a nice compact sort of structure. But the difference between them and lists is that they are immutable. And what does this mean? It means that they cannot be changed after creation. And even if you look at the format, you can tell that they're pretty similar to lists, right? Just swap out the square brackets and replace them with parentheses. It's the same deal, right? So here's an example of a tuple, 1, 2, 3. Same as lists, you can store, you can create a tuple with different data types in it. But the difference between this and a tuple is that if you recall with a list, we can redefine any of the elements of the list to have, we can redefine any of the elements of the list to be something else, right? If T were a list and we said T, the element of T at position 0 equals 4, the program would be like, okay, great. Now, whenever I want to index T at 0, we're going to put 4 now. Fine. But now, if we try this with a tuple, this doesn't work. And I guess we could do a live example of this. If if you guys have like the collab that I have shared in the folder with you pulled up, I know there was a little bit of difficulty like setting this up, so I wanted to run through that a little bit. Here's the like Google folder link that I shared a little bit ago. Essentially, you can make a copy of this for yourself, so it doesn't like end up kind of trampled with the stuff that I work on as we do these lectures. If you just hit that and then click. New folder, get link, share color. It might be a little weird because I actually own the folder. Move to add star. Okay, I'm gonna be honest. Yeah, perhaps you can download it and then re-upload it into the file. Okay, fair and understandable why that might have been an issue. But regardless, once you have your own copy, yeah, once you have your own copy and you have it on actually, wait, this is exactly why I have everyone on screen today. Hi. How was your experience with like working with this? Last I checked, the copying of folders was like pretty intuitive, but perhaps that might have been an oversight on my part. Did you guys have what was your experience with like moving the collabs and like working with them on your own?
Sorry, can you hear me?
Yeah.
So I couldn't figure out how to copy entire folders, but it's like easy to copy individual files. So I just copied some of like the individual file collabs, and that was fine.
Okay. All right. Yeah, I think that's probably the optimal way to do it without like doing this entire mumbo jumbo. The way in theory that you could copy the entire folder is the way that I'm going to do it now, is that you can like zip it. No, I would not like to buy WinRAR, sorry. Zip it, unpack it, and then like re-put it up onto Google Drive. And then here it is for you, essentially in all of its glory. I am going to write up more of an explanation on how to do that. So thank you for the feedback. For whoever gave it, that's noted. Yes. All right. We don't have to keep doing that. Yeah, we'll write up an explanation on how to do that. But thank you for bearing with us and like copying over the individual files. That's a good call. Anyhow, so once you get to that part, that just automatically does it for me. But you can right click on it and click open with Google Collaboratory. If that's not there for you, you want to click connect more apps. And then I'll bring you to this screen and then just look up Collaboratory. Yeah, click on that, install it, add it to your drive, whatever, and then right click, open with Google Collaboratory. That should be there for you right there. Great. Okay. As per usual, you can skip the grading session because this is not a class and your GPA is going to depend on this because we don't even have that power. Okay. Yeah. So here's an example, right? We're creating a tuple. It's simple as creating a list. Instead of square brackets, we're putting like parentheses around it. It can be, we can put anything in here. A, 1, heck, we could put another tuple in here if we wanted to. It doesn't really matter, right? It's all valid. Any data type, put it right in there. The only difference is, if we made this a list instead, right? Here is our example. If we made a list instead, lists are mutable, which means that this would work. Right. Right. That's a trick with collab. You have to like rerun every cell every single time you change it, or else it just doesn't recognize that it changed. Yeah. Anyhow, so if we make T a list, and then we say the 0th element of T is 4, and if we want to look at T again, now the first element of T is 4. It's no longer A. That's to say that lists are mutable. Tuples, however, are not mutable, as you saw with the error message that just came up. If we try to do this and we make T a tuple, we can't change just the 0th element. Does not support item assignment. Great. Okay. So quick little live demonstration. Tuple properties, you'll see that it ends up being very similar to lists, right? We can call length of T once again to get how many elements are in it. We can index at specific elements. It's still zero indexing, so the 0th element of T is confusingly the word 1, but and then if we slice it, we can get the same deal. If we slice like this, we get the 0th element and the 1th element, the 0th element and the 1st element, nicely wrapped up in its own tuple. There's that. So pretty much the same as lists, same deal. Built-in tuple methods, once again, lists, right? We use .index if we want to get the index of whatever value we put in. So if we call t.index of 1, what is the index of this element 1? Well, it's in the 0th position, so the index is 0. That'll give you back 0. Dot count kind of is what it is on the tin. How many times does the argument occur in the tuple? How many times does the word 1 appear in T? Well, just once, so we get 1. All right, now we're going to do a little bit of live coding examples. So before I start on that, does anyone have any questions? Oh, hi. There's chat. Daniel told me to come here. Thanks, Daniel. So I think I made copies of files like Livia was just saying, so I'm unsure what's going on with Colab. Okay, maybe it's worth the time to explain what the deal with Colab is. So the thing is, Python is Python, if you're working on non-Unix computers, which is to say if you're working on Windows computers, it doesn't come with it. It's a little complicated to set up. It's a whole ordeal. Personally, I've had a bunch of issues just making sure my environment variables with Python are straight. It's a whole ordeal, and it's not very accessible. And if you're just getting started into computer science, it's kind of a whole thing to set up Python on your own computer. The thing with Colab, though, is that it's nice in that Google came to us, and not us, but Google said, hey, we want to make a more accessible way for people to actually use Colab, this, that, and the other reason. They had plenty of reasons to do this. So let's make a system that allows people to work with Python online, and not just online, in a way that they can collaborate with each other, just like the rest of the G Suite. And that was a cool thing of them to do. And so they came up with Colab. And here's what it is. Basically, Colab lets us mix Python cells in with just regular text cells. So here we have text, and then here we have Python, and you can do whatever. Basically, every time you run a cell in Colab, and just to run, you can either hit Control Enter, or you can just hit the Go button to the side. That's like running a line in Python. So every time I hit Go, that's me. It's equivalent to in Python, I have run this line. And then the next time we run it, the next cell that we run, it's equivalent to running that cell in Python. So you'll notice that I don't know, maybe an example here would be if I make two code cells and I say A is equal to 1, and then I have to print A. If I hit print A without running this cell first, it doesn't make sense, right? Because we never ran this line, even though it exists. It's basically the same thing as not running the line in Python. So it doesn't know what A is. Fair enough. Yeah. On the other hand, if we want to run this first, now A exists, print A, now it returns us 1. That's kind of what the deal with Colab is. It's basically a nice environment that we don't need to set up Python on our computers, and we can just work on it online. Does that answer your question in chat? Hopefully. Okay. Great. Cool. Thanks. Okay. Any other questions with tuples, Python, whatever? I'll talk about anything. If not, we are going to move on to this. We don't grade. That's whatever. I'm also going to change this from ant to 1 to t because I don't want to type that out. Great. So what's the deal with this? So right now, t is nothing. That's what none is in Python. So if we print out the type of t, it's of course going to give us none type. That makes sense. Great. How do we make a tuple? Help me out, guys. I forgot how to do it. Seth, Livia, anyone in chat, what's the syntax? How do we do it? Yeah, give me some advice.
It's just regular parentheses, right?
Okay, great. And we can just put whatever we want in here? Yeah, we just put whatever we want in here. Actually, we don't even need to put anything. It already recognizes it as a tuple. Great, but let's actually put some things in here. Let's put A, let's put B, let's put C, let's put another tuple of 1, 2, and 3. Heck, let's put a list. Why not? We know nothing. We can do whatever we want.
So if
Yeah.
we had just defined it with nothing in it, because it's immutable, does that mean we can never change it to have something in it?
Yeah, that's a good point, actually. Let's try that. Let's say T of, I mean, it doesn't even have a 0th element, so it's going to, like, yeah, actually, it doesn't even have a 0th element. So I'm pretty sure if this was even a list, we're going to kind of get some pushback on it. Yeah, list element index is out of range. But especially since it's a tuple, it's going to complain even more, right? Because not only is it out of range, it's also immutable. So that's like really not allowed. You might be wondering, like, what's the point of tuples? They just seem like less cool versions of lists because we can't even change them. Good point. Sometimes, though, remember, there are situations where we just don't want things to change. And if we use a list and we're not careful, things inside of it can get like moved around, changed, whatever. Tuples guarantee that that'll never happen for us. And that's like a nice guarantee to have sometimes. So yeah, that's the motivation behind tuples. But anyway, here we are. We're just like making a random tuple. That's fine. It's still of type tuple. We want to print it out. I mean, it's just going to be that. How do we, let's say I wanted to print out the number 1. How would we do that? Any thoughts? 1, remember, is right here. And it is within this tuple, which is within this tuple. So it's a little complicated. But let's say I wanted to access just the number 1.
So I think it would be, you'd want 3 and then comma 0.
Like this?
Yeah.
Okay. Let's try that out. I'll tell you what, though. You're almost there. You're very nearly there.
Oh, there's no comma, is there? It's double indexed?
Like this?
No, with another pair of brackets.
Like this?
Yes.
Great. So maybe to clear up the motivation for why you need to double index that, I'll just print out T of 3. And this will print out, 1, 2, 3. And if we want to remind ourselves what this is just, I mean, not that. This is just another tuple, right? And this is a tuple. This is a tuple 1, 2, 3. And so that's just what T of 3 is. And if we were to take this as the result that came out of it, how would we access 1 from this? Well, we just like take this as its own thing. To access 1 from it, we want to index it at 0. Does that make sense to everyone? Cool. All right. What else do I really want to talk about with regards to tuples? Oh, right. Let's try this one on the side. What do you think happens? Oh my lord, my typing. What do you think this will give you? Any takers? Kind of weird, right? Because like if there was only 1 C, obviously this would just like return 0. There's 2 C's. Yeah. I guess to be fair, I haven't given you any reason why. Okay, let's see what happens. It'll give us 0 again. Okay, that's a weird trick. What if we did that? It gives us 1. So the lesson here is that index gives you the first time the element occurs. Yeah, that's something to keep in mind. Sometimes I use index as a trick, but then I have to remind myself it's not foolproof, because if the element occurs multiple times in the list or tuple, it'll only give you the first one. So yeah, and reasonably, if we give count, that should give 2, right? Okay. Yeah, that's the deal with tuples. Everyone good to move on? All right. Okay, so that's a data type that we now know about. That's pretty similar to lists. We're moving on. We're pivoting to something a little more complicated called dictionaries. So what are dictionaries? Dictionaries are the data type that store a mapping of key value pairs. What does that mean? Let's look at this example. In this dictionary, we associate each key with a different value, right? Key 1 is associated with value 1. Key 2 is associated with value 2. And keep in mind here that key 1 and key 2 are strings. There are specific values that can and can't be keys. Strings can be keys. Numbers can be keys. Really, the trick with what can and can't be a key is 2 things. First of all, you can't have 2 of the same key, right? Because then if you try to access a value, by the way, you access a value by doing indexing, but instead of with a number, you index with the name of the key, and that'll give you the value associated with it. You can't have 2 of the same keys, right? Because then, like, what does the computer or what does Python, which value does Python give back to you? And 2, keys cannot be mutable. Keys have to be immutable objects. Great. Yeah, we'll see this in action in a second, but hopefully that makes some intuitive sense. Here's the other nice thing with keys. There are some restrictions on what, here's some more information about dictionaries. We have some restrictions on what can and can't be keys, but we don't really have restrictions on what can and can't be values. Anything is pretty much fair game. We could have a number, 1, 2, 3. We could have a list. We could have another list. We could have a dictionary. We can have a tuple. We can have a string. We can have whatever we want. And this ends up being like a more complicated thing than a list or a tuple, because now we have associations between one thing and another thing. Another thing to keep in mind with dictionaries is that if you go back to tuples or even lists, there's an inherent order to it, right? Like 1 here is at index 0, 2 is at index 1, F is at index 2. So if you ask for like the 0th element, 1st element, 2nd element, there's an order to it. 1 comes before 2, which comes before F, which comes before 3.14. With dictionaries, it might look like there's an inherent order to it. It might look like key 1 comes before key 2 and key 3. But if you look at the computer's memory, there is no order to it whatsoever. The only thing that matters with a dictionary is that 1, 2, 3 is associated with key 1. And the list 12, 34, 56 is associated with key 2. There's no order. The only thing that keeps it organized is these associations between keys and values. Okay. So once again, indexing looks pretty much like it does with lists and tuples, except it's with the names of the keys. And then multiple indexing, just like before, D of key 3 will return to you this list when I index it at 0. We got item 0. Sure, fair enough. Great. So even if keys can't be mutable, dictionaries themselves are mutable, which is nice. We can go in and sort of do whatever we want. The way that we do this is that we just index. It's pretty similar to lists, right? We index at whatever key we want, and then we set it to something else. This means, unlike with tuples, and honestly, unlike with lists as well, we can create new key value pairs, right? Remember the remember the experiment that we sort of just tried with an empty list, and we tried to say like, a list of 0 is equal to some element. Granted, we could use the append method there, but if we just try to add a new element by indexing, it doesn't work. This is a little different. If we try to create a new element, if we try to create a new key value pair by indexing with a key that doesn't exist, it'll add it to the dictionary. And yeah, so this ends up getting pretty complicated. Another case for why we need computers to do things, because it's a lot for the human brain to keep track of. We can nest dictionaries within dictionaries, which is kind of like the logical leap of like nesting lists within dictionaries. when I say values can be anything, I really do mean anything, which means we can put more dictionaries as values of keys in dictionaries. Yeah, we are going to do more of that in a second when we get to like a live coding session. Great. Last thing I want to talk about, is this the last thing? Yeah. Last thing I want to talk about is that dictionaries have built-in methods that make it easier for us to use them. If we want to get a list of all the keys, well, technically it's not really a list, it's iterable, but like for all intents and purposes, it'll give us back a list. If we want a list of all the keys, call d.keys, sure. If we want a list of all values, d.values. And remember, this will spit it back to you in an order, but I really encourage everyone to think of this order as arbitrary. Again, in computer memory, there is no order of key 1, key 2, key 3. It's just this association between 1 and key 1, 2 and key 2, and 3 and key 3. The order that it spits back out will happen to be the order that you defined it in, but semantically to the computer, it doesn't matter. Anyway, same goes for values. And d.items, it'll return to you a list of tuples with the key value pairs in the form where everything is wrapped up in a list and each of the key value pairs are in tuples. Okay, that was a lot. We're going to get to more live coding in a second to look at the syntax and the semantics and all that, but does that conceptually make sense?
Yeah.
Okay. All right, cool. Let's break it down. Dictionaries. Yeah, now try this. I will try this. Okay. I'm gonna delete all that. Okay, so they ask us to do a few examples. We'll look at these after we have talked about this. So let's make a dictionary first. Let's call it D. Dictionaries we wrap up in curly braces, and let's create a key value pair. The way we do that, we have the key on the left and then colon and then the value. Let's say the value is this. Great, now we have a dictionary. So let's add something to the dictionary. Actually, cool. Let's start out with an empty dictionary. Let's say I wanted to add this to the dictionary. How would we do that? Well, if we remember the thing, the way that we add a new key value pair into a dictionary is by indexing the dictionary at the key that we want to add, and then assigning it to the value that we want to add, right? So if we print D before adding, and then we print D after adding, this should, yeah, right? Cool, that should be pretty clear. But okay, let's not like add everything to the dictionary like that. Let's save ourselves some time. If we want to add another key value pair to the dictionary, we just add a comma and then we go whatever. Let's make this a tuple just for fun. And just for fun, let's make this a dictionary. Great. This is gonna be a really fun dictionary. Yeah. Okay. Great. What do I want to do with it? Let's look at a few examples. What are we talking about? Yeah. How would we get the dictionary associated with C? What do we need to index D by? I feel like I might have revealed the answer a second ago. Whoops. Yeah, what do we index D by?
2.
Okay, let's try that. All right, we run into a bit of a snag in that dictionaries are different. Like if this was a list or a tuple, then we'd be like all set, right? Because this is in the second position. The problem is that like dictionaries are fundamentally different in that they don't operate off of any sort of order. So like the order that I put these in is completely arbitrary. The only thing that matters to the dictionary is that this dictionary is associated with the letter C. So it doesn't care what position it's in. So if we say D of 2, it just doesn't care. It's like, what is position 2? This is not a thing to me. All it knows is that like, okay, I have a dictionary associated with the letter C. So I'll give you one more try. what should we index D by?
C.
Like this?
Do you want to put it in the like little quotes?
Cool. Yeah. Sorry. Trick question. Yeah, you're right. There we go. What if I want to get the letter Z from it? What if I want to just print out the letter Z?
Would it be C index 2?
2. Let's see what happens. Okay. Weird. Why 2?
Because don't we have 0 indexing? 0, 1, 2?
Right. Okay. So let's recall what D of C is. It returns to us a dictionary. And here I've purposely done something a little tricky, so apologies. But remember that this is still a dictionary. If I had set it, let me make an example. If I had set it to be like, I'd set it to be like this. And we did what you just said, that would work. I guess it wouldn't work. It would work exactly like you just said. However, since it's a dictionary, let's remind ourselves that to index from a dictionary, we need to call the name of the key. We can't call the position because position is arbitrary to a dictionary. We need to access the element by calling the name of the key. And now I've named the key 1, 2, and 3, which is a little tricky because the names of the keys don't correspond to what seems to be their 0th indexed position, right? Because like if this was a list, X, Y, Z, X would be associated with 0. I've assigned it to 1 because I'm full of nonsense today, I guess. Oh, whoa, where did everything go? Hello? Okay. All right. Yeah. So what we actually want to do is not to index by position, but we want to index by name of the key. So what is the name of the key associated with the letter Z?
3.
Yes, 3. Also, thank you, Charlotte in chat. Yes, 3. So did that work? Yes, that should work. Okay, great. Hopefully that breaks it down a little bit for you all. Maybe it might be good to look at a few methods. These are pretty self-explanatory. Maybe self-explanatory is the wrong word. These are pretty intuitive. If we want to look at d.keys, yeah, this is what I mean. Like technically it's not a list. Technically it's like a dict key items. This is getting like really into the weeds of it. It's technically not a list. But it basically functions as one, and if we want to convert it to a list, we can do that pretty easily just by calling the list. Point is, if you want a collection of the keys of the dictionary, we call it d.keys, and once again, this will return to you in the order that you input them into the dictionary, but I caution you against using that ever because remember, dictionary key value pairs are not inherently ordered. So yeah, keep that in mind. Same deal for values. Yeah, 1, 2, 3, 1, 2, 3, 1, whatever. I'm pretty sure it'll allow for repeat values as well. So, that's cool. And then d.items. Yeah, whatever. This might not seem like super useful now. But as we go on to talking about loops, literally in a few minutes, the motivation for doing this is like it'll become clear. I promise you. So yeah. Okay,
Wait,
dictionary.
sorry.
Yeah.
D dot items just prints the whole thing, the whole dictionary.
Oh, right. So d.items, it returns so d.items in itself, and just to be clear, like d.items doesn't print any. Okay, this is a really bad example because Python is like Google Colab is too good for us in that it just like if we just put something in there, it'll if we put something in the last line, even when we don't actually want to do it. So my point is d.items doesn't actually print anything. It returns something, which is to say that if we like say that x is equal to d.items, we can do this, but we can't say that x is equal to print that because like this is not the points that I make are destroyed every single step of the way. Okay, I guess print is like my computer science knowledge, please. The print object, this will return a function. So technically this is like a callable object that I guess we can store, but like inherently it stores a process, right? Like if within X, it stores the process of doing something. It doesn't store like something in itself. That's kind of really getting into the weeds of it. For all intents and purposes, just imagine that like X doesn't store anything, it stores a process. It's a callable, technically. Right. Which is, yeah, go ahead.
So would print D and print D.items return the same thing?
Oh, good question. Let's actually try that. So here's print D. Great. Here's print D.items. Okay. So they're slightly different, and I'll point out the differences here. So print D, this is just our dictionary as it is. D.items is, if we look at it, ignore the fact that it's wrapped around the words like dict items, but this is a list, right? Because, you know, we have the brackets on the left and right denoting that it's a list with like different elements. What are the elements? The elements are the key value pairs wrapped up within a tuple, right? If we look at it here, the first tuple is A, which is the first key, and then the value 1, 2, 3 in a list, right? The second element of the over like the entire list is the key B and the values 1, 2, 3. So the difference is slight, but it matters, and I will show later once we get to loops why it matters. Okay. I feel like I was about to say something. Oh, right. Just to wrap up on Livia's question, my point is d.items does not print out anything. Like if it did print out something, then it would print out here. The point is d.items is a collection of things. It's the collection of items. Yeah, it is the list itself. It's not the process of printing it out. It's just like the thing. That's kind of a high level sort of comment, but yeah, imagine if you call d.items, this doesn't do anything, but it gives something. Like d.items is a thing. It doesn't do anything, but it is a thing. Okay. Great. Any other dictionary questions before we move on to loops? I promise some of this stuff about like d.items and d.keys and d.values will be a little more clear when we talk about while loops and for loops. I don't know if they motivate it exactly in here, but I will like come up with, yeah, I'll come up with a few examples for that. These are some nice brain teasers. I don't want to like run over time though, because loops are can be a lot. So we'll come back to these in the end if we have time. Okay, loops, wonderful. This is really like, to me at least, the meat and potatoes of like when it really starts getting into why we need computers to do things and why we can't like just do them ourselves. So loops are a sort of control structure which allows us to run specific lines of code over and over again. So we'll see examples of these later, but for now we can focus on two types of loops. One is called the for loop, and one is called the while loop. So for loop performs an action for every element in a sequence. And the format goes like this. For, and then you, okay. For item in my list. What does this mean? It means we have some iterable here, which in this case is a list called my list. What is an iterable? That's kind of a weird question. All you need to know about an iterable is that there is like, the computer can make sense of the idea that there is one element and then the next element and then the next element and the next element. There's like some inherent order to it. And keep in mind, I'm using a very specific phrasing here. There's an inherent order to lists. There is no inherent order to dictionaries. That'll come into play in a second. Okay, so an iterable is something that has like an inherent order to it, and the program can reasonably go from one element to the next element to the next element. So for item in my list then considers for every time it runs through whatever lines of code in the for loop, it'll take item to first be the first element in the list. And then item just becomes, in this case, 1. And it'll run whatever is in the for loop. So print 1. And then once it's completed the code, it'll go back and say, okay, now item is the next element in the list, right? So then it'll be for item is now 2, print item, it'll print 2. All right, after it's print 2, it goes back up and it says, what is the next item in the list? It's 3, print 3. What's the next item in the list? 4, print 4, so on and so forth. Actually, this might be fun. With that logic, what do you think happens if we run this exact line of code?
It prints out the numbers.
I mean, yeah, pretty intuitive. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. And I think this little blurb explains it really well. If we didn't do it like this, we would have to, we would literally have to go like print my list 0, print my list 1, and so on and so forth. That's a waste of time. Programming, fun fact, inherently lazy job. Programmers try to do as much as possible with as little effort as possible. That's like the whole shtick of it. So anytime you can get a programmer to write less code or to write more efficient code, the happier they are. And hence we have this. Cool. Yeah. All right. We have a question in chat. Could we repeat what dictionaries are used for? Fair question. Dictionaries primarily are used for whenever we want to associate, whenever we want to build associations between one thing and the a name. If we want to give a name to an entire thing. That's not really clear. Let me motivate it like this. Not to like dwell too much on dictionaries because there's but this is kind of a good question. And by kind of I mean it's a really good question. All right, it's good to motivate things. Let's give an example of like an actual dictionary. All right, Apple. This is how actual dictionaries work, right? We have a word and we have a definition. A tasty fruit. I can't spell. Right. And then what else? A banana. Another tasty yellow fruit, right? We can't really do this with like lists, right? If we try to imagine semantically this making sense in a list, there's like not really a way to do that. Like we can say apple is a tasty fruit, but there's not really like association between a tasty fruit and apple, right? So only through a dictionary can we build these associations right within our structure. And the benefit of this is that if we want to grab a tasty fruit, or even like if we want to know what is the definition of an apple, all we need to do is call dia.apple and it'll return to us its definition. So that's a really quick motivator for dictionaries, like an actual dictionary. That's probably where it got its name from. Anyway.
I've got a question about the loop that we just made.
Awesome.
When we said for item, was item, is that us initiating a variable, or is item part of this thing?
Yeah. So this ends up becoming like a discussion about scope, which is to say like for item in my list. Then item is associated with some element of my list and whatever element it is depends on like how many iterations we have gone through the for loop.
But could we have used any word for item?
Oh, absolutely. Traditionally, I'll use like the letter I most of the time. I stands for iterable. But the point is, no matter what you name it, it still stands for some element of my list. And the whole thing here is that you'll want to note that once we're outside of the for loop, item ends up storing just like whatever the last thing it was, right? The last thing item was in the for loop was 10. So now item is 10. Even outside the for loop. Make sense? Cool. All right, we're gonna keep moving. For loops too. This is kind of a jumble of code. What is the point here? For loop. Oh, right. Okay. So we're motivating for. So like, what can for loops do? We're actually just going to be looking at the code here then. What can for loops actually do? Here's an example of what they can do. Let me ask you the question, like, what is the sum of all these numbers? That'd be kind of hard to do without this. We could say like print my list at 0 plus my list at 1, and so on and so forth. Again, that's a hassle. Who wants to do that? Here's a sort of clever way to do it. We're going to start with some variable equal to 0. Well, we'll call it total. And then we're going to iterate through my list for item in my list. And then what are we going to do? We're going to add it to the total board. Are you guys familiar with like the plus equals notation? Yeah, okay. So yeah, total is equal to total plus item. Actually, I'll just write that explicitly because that's probably a better way to do it. Total plus equals total plus equals item. So let's think through what this is going to be. This is a really good computer science activity, thinking through what your code is going to run before it actually comes out. So I'm asking you, I'm going to ask, through any given iteration, what is the value of total? And we're going to print total at the end. Okay. Well, on the first run through, well, total in the beginning is 0. So total is 0 here. After total equals total.item, we now have that total, which is whatever total is going to be, going to be equal to, total is equal to what total was before, which is 0, plus item. Item, we're starting out with the first element of the list is 1. So now total is 1. Okay. So what next? Now item, we run again. Item is the element after 1. So now item is 2. And total is 1. So now we have that total is equal to total, which is 1, plus item, which is 2. Everyone following so far?
Sorry, I'm not exactly. What is the calculation that you're trying to get it to run?
Sure. I'm trying to calculate what is 1 plus 2 plus 3 plus 4. I'm trying to get it to add together all the elements in my list.
Okay,
right.
Sure.
Yeah. So the idea here is that we're going to be incrementing the variable total for every element in my list. Actually, this might be kind of clearer if we run this. Yeah. Okay. So this is going to be kind of clear. Print and print. Actually, how am I going to do this? We're going to do it like this. Okay. Item is equal to item total is equal to total. Excuse me. Okay. Great. So each of these lines is associated with a run through of the for loop. Okay. So the first time we run through the for loop, item is equal to 1. Makes sense. That's the first element of my list. And total is equal to what total was before, which is 0, plus item, which is 1. 0 plus 1 is 1. Cool. Okay. The next time we go through the for loop, item is the next element in the list. The next element in the list is 2, right? And we call total is equal to total plus item. What is total? Total is 1. Item is 2. 1 plus 2 is 3. So now total is 3. Okay. Item is now the element after 2 in the list. So item is 3. Item is 3. Total is 3. So the new value for total is equal to total 3 plus item 3 is equal to 6. And so on and so forth. Does that make sense? Okay. And we end up getting this like loop, which, I mean, it becomes pretty clear, right? Like we're adding all the numbers of all the items together, it ends up being, right? Because what? This 10 is equal to 4 plus 6, but 6 is equal to 3 plus 3, but 3 is equal to 2 plus 1, and 1 is equal to 0 plus 1. Basically, kind of a fancy way to add all the numbers in the list together. Does this make sense? Okay. All right. So that's the value of lists, right? That's the value of loops. It gives us like clever ways to work around questions that we maybe wouldn't have been able to do, or problems that we maybe wouldn't have been able to take care of earlier. So now if we want to print out this, if we want to print out the total, we just do that. Don't tell anyone, but you could also just do this. But it's a good motivating example, even though there is a function within Python already to do it. It's a good motivating example. Anyway, so that's that. We'll do one more example of what you can sort of do, what you can do with the power of lists. They say we want to print out all the odd numbers in a list. How would we do that? Well, anytime you see like, actually, yeah, you know, I'll leave it up to you guys. Any thoughts? How are we going to print out only the odd numbers in the list? Here's a slight hint. We're going to have to... The nice thing about this is that now, instead of working with the list as a whole, we can work with each individual item in the list. Right? That's the nice thing about for loops. Or loops in general, we can now like itemize the stuff in an iterable. But beyond that, does anybody have any ideas? Okay. That's fine. This is, I mean, loops are really like the big hurdle. But we know that we want to print out the number at some point, right? So we have to have a print item in here at some point. But we only want it to print sometimes. But when do we want it to print? We want to print out when it's odd. So in pseudocode, we say if item is odd, then print. Then print item. So this is the ideology, or this is the thought process of what we want to do. So how do we evaluate if item is odd? Well, an item is odd when its remainder, if item's remainder is 1 when divided by 2. Right, because if its remainder is 0 when divided by 2, then it's even, and we don't have any decimals in here. So if the item's remainder is 1 when divided by 2, then it's odd. Right, how do we implement this in code? Right, if you recall from last time, we have to use if, and then item divided by 2, or modulo 2 is equal to 1. Cool, let's see what happens. Oh, look, odd numbers. Okay. Does this make sense? So the thought process here then behind working with loops, especially the for loop, is we want to think of it in a very itemized process. We want to look at, after we call for item in my list, then we are working with individual items of my list. So now we can think about, okay, if we have a specific item in my list, what do we want to do with it? Well, we only want to print it when it's odd. So if it's odd, then print it. That's the thought process. Okay. Cool. I'll leave a note for myself. Okay. Great. So that's enough about for loops for now. More loops. Second type of loop. While loops. While loops will continue, or it's the same idea as for loops in that it'll continue running the code inside the loop, but instead of running it for every element in a list or a tuple or an iterable, it'll just keep running until it'll just keep running while a condition is met. And by condition, I mean like some Boolean variable, right? It'll continue running so long as whatever comes after it is true or evaluates to true. We'll have to take a look at these. Okay, so let's take a look at some live examples of this. So first and foremost, before we even do that, let me put my money where my mouth is. While true. Okay, this is something you should really not do as a programmer, but I'm going to break a few rules to demonstrate something. So what am I saying? A while loop will continue running so long as the Boolean expression that comes after it evaluates to true. Obviously, true evaluates to true, and it will never not evaluate to true. So this is going to print infinitely. And let's watch collab crash. Okay. Yeah. It's still going. It's just going to keep going until I tell it to stop. So I'm going to tell it to stop. So yeah, if I didn't tell it to stop, it would just keep going forever because true never becomes false. It's a weird sentence. But while the Boolean expression that comes next to while evaluates to true, then I'll just keep running the stuff inside. And when it evaluates to false, it won't evaluate the stuff inside. So that'll run infinite times. This will run 0 times because it evaluates to false. Make sense? Okay. So you might be wondering, okay, Bruce, if your options are either to run it infinite times or run it no times, what is even the point? The point is we can write something a little more complicated for the expression next to while. So here's an example. We start out with some counter variable. Let's set it to actually 3. That's probably easier. And we say while count is not equal to 0. Okay. So what? The little trick here is that we modify what count is within the while loop. Okay. So what does that look like? So what does that look like here? So we start out with count is equal to 3. And while count is not equal to 0, it'll print count, and then it'll decrease what count is. So let's imagine what this output would be. First time around, count is equal to 3. Go through the while loop. Is count equal to 0? No, count is not equal to 0, so this evaluates to true. Therefore, we can go into the while loop. Print count. Well, count is 3. And then now count is equal to count minus 1. So count is going to be 2 now. We go back up. Count is now 2. Is 2 not equal to 0? Yeah, it's not equal to 0. Great, so we can go inside the while loop. Print count. Count is 2. Now, what is count? Count is equal to what count was before, 2 minus 1. 2 minus 1, 1. Count is now 1. Is 1 not equal to 0? Yeah, 1 is not equal to 0. Great, so we can go inside the for loop. Print count. Count is equal to 1. Count is equal to count, what it was before, 1 minus 1. Count is equal to 0. Go back up. While count is not equal to 0, is 0 not equal to 0? No, 0 is equal to 0. Therefore, it doesn't go into the while loop again. So if we print this, hopefully it should give us 3, 2, 1. It does. Great. I just said a lot of words. Everyone following so far?
Sorry, what's the exclamation point? Like count exclamation point equals 0.
Good question. Thank you. So we know that like x is equal to 1. This singular equal sign means assignment. Now we're saying that we assign 1 to x. Let's comment all this out real quick. A double equal sign is a Boolean expression, right? It's asking us that's not really fair. Double equal sign is equivalency. It's asking us, is 1 equivalent to 1? And that's, 1 is equal to 1, right? So this is the same thing as saying 1 is equal to 1 is equivalent to true, right? Because it's just asking us if 1 is equal to 1. Now, what if we want to say that two things are not equal to each other? That's where the exclamation point comes in. My exclamation point button is broken. There we go. So this is now asking, is 1 not equal to 1? Well, 1 is equal to 1. So saying that 1 is not equal to 1 is false. So this should give us false. So if you imagine that double equal sign is equivalency, exclamation point equal sign is the opposite of that. Cool? All right. All right, so that's while loops. We'll move on. Should I talk about it? Yeah, let's talk about it. We could talk about it. We're gonna return back to this idea. We're gonna go back to the while true. So the idea is we could print this an infinite amount of times. We're gonna go back to print high. There's a little cheat, and I called it cheat because I encourage you not to do it too much. But if you want to break a while loop, or if you want to break a for loop even before its natural termination point, you could use the keyword break, right? What does this do? While true, true is true. Prints high, it sees the word break. It says, we're getting out of this loop right now. Yeah. Yeah. The one secret that no computer scientist wants you to know. Okay. Anyway, so what are they doing? What was this before? 1. Yeah. So essentially this prints high. Let's not have it be 10. It prints it 3 times, right? Same process as before. Count is equal to 3. 3 is not equal to 0. High. Count is not equal to 2. 2 is not equal to 0. High. Count is not equal to 1. 1 is not equal to 0. High. Count is equal to 0. Count. This is not true anymore, so it breaks. While loops. Fascinating. Great. We're gonna move on. Yeah, we did that. Okay, this is kind of interesting. We can see how a while loop interacts with other objects. Let's say we wanted to make this list. My lord. Okay, make this list. How would we do that? Well, we could type it all out, but again, we're computer scientists now, so we don't want to because we're lazy. What do? We can, well, we notice that these are just like the numbers counting down from 10 to 1. So another way to think about it is that we could start out with an empty list. Or here's another way to do it. This is how they did it. Either is valid. We can do whatever we want. Let's add some variety into our lives. And we could start with some count variable equal to 10. And then now we say, while count is not equal to 0. And the idea here is we're saying, okay, we want to decrease count by 1 every time. But before we do that, we want to add count to the list. Yeah. So if we trace through what this should be, we start off with the empty list. Okay, count is 10. 10 is not equal to 0. Great, we're allowed in. Append 10 to the list. So after the first run, it'll be some element like this. The list will look like that. And then count decreases. Now count is 9. 9 is not equal to 0. We add 9 to the list. Great. Now count is 8. 8 is not equal to 0. Up until like we get 1. Right? And then 1, count is equal to 1 minus 1 equals 0. Then we don't go through the list anymore. We run this, we get that. Cool. Does this make sense? Okay. Let's move. Oh, they do talk about break. They do talk about. Okay, that was being dramatic. Whoops. So the interesting bit about. Oh, I'm not moving very quickly, am I? Okay. The interesting bit about while loops and for loops is that they're actually interchangeable. Kind of a nuanced detail, but anytime that we could use a while loop, we could. Yeah, anytime we could use a for loop, we can use a while loop, and anytime we use a while loop, we could use a for loop. I don't know if I said that right, but I hope you guys get my drift. What's an example of this? We had let's do an example of before of like our list, like our whole adding every element in the list activity. Yeah, let's do that, but now with a while loop. Right. So what are we going to do? We have our total as before. We're going to initiate another variable called num. Num is going to end up being what we are indexing the list by, because we no longer can freely just say this element of the list and the next element of the list and the next element of the list. We actually need to create another variable to index the list. And then the count is just the number of times that we end up going through the loop, as before, right? How many times do we want to go through the loop? We want to go through the loop for each element of my list. How many elements are there on my list? That's the length of my list, 10 in this case. So while count is not equal to 0, well, count starts off at 10, right? So while count is not equal to 0, we add to total my list at number, right? Number starts off at 0. My list of number is equal to the first element, 1. And now we're doing this little thing where we're saying we're incrementing number, right? Number is just the index that we're indexing my list at. Number is equal to number plus 1. Num is equal to num plus 1. So now num is equal to 1. This is the same thing as we did in the for loop when we said instead of item just doing it for us and saying that the next item is now 2, we have to add to number. So we move on to indexing the next element, right? Because now number is equal to 1 instead of 0. And if we call my list at number, which is now 1, then we get the index. We get the element after 1. Make sense so far? Okay. So that's the ideal number. And once again, with count, we're decreasing count. So now count is 9. And it sort of makes sense to say that like every time we go through this list, number increases, which means that we're looking at the next element of my list, and count decreases. And once count is equal to 0, we're going to stop going through the while loop. So if we imagine, once again, I wonder if I kept it. I probably didn't keep it. If we do the sort of situation again where we say print num count total. And we looked at it for each iteration, right? Number is equal to 0, count is equal to 10, total is equal to 1, right? Because because my list at 0 is equal to 1, so we add 1 to 0, we get 1. Count 10. Count just keeps going down and down and down and down until it hits 0, in which case it tells us to stop. So that's nice. It tells us to stop. So once we know where to stop, we basically just do what we did with the for loop, except we need like an index to keep going up, because unlike the for loop, we don't just get to like freely move on to the next element. Does this make sense? Okay. So that's the explanation. Anything that we could do with a for loop, we could do with a while loop. This might look cumbersome, which is why there are like situations where it's better to look at a for loop than it is a while loop. Generally, when you're working with iterables, don't use a while loop, use a for loop. It's just easier. But it's good to know that the two are basically interchangeable. Yeah. So we talked about break. Continue. It's like the opposite of break. It's basically whenever you run into the word continue, it ignores everything in the loop that comes after it. It ignores everything in the loop that comes after it. So just to give an example, before continue. This is like a super explicit explanation. after continue. Yeah, it only ever prints out before continue, never prints out after continue, because once it hits continue, it just goes back to the top of the for loop. It ignores everything that comes after. It's like, oh, continue, I will continue. Just none of the stuff after. I'll do the next iteration of the loop. Make sense? Great. Now try this. Oh, I'm running out of time. How did Amy do it? Okay, these are okay. I want to talk about functions and I want to talk about modules and packages. So we will get back to that. 2S. Okay, we're gonna. This is why we're testing the curriculum. So this is good. Catch these now. Okay, functions. What's a function? Basically the idea is sometimes we want to do a process like a million times, but we don't want to have to write out that entire process every single time, because once again, the less coding we do, the better. So how can we do that? We write something that's called a function. And so what does a function look like? How do we use a function, first of all? Because Python has some built-in functions given to us already. The idea of the function is that we call the function name, and then we pass in parentheses, arguments to the function. What's an argument? It's basically something that the function takes and works with to give us something else. Parameters, placeholders for variables within a function. Yeah, more on parameters later. I guess, no, that's a bad habit. Like for now, for all intents and purposes for this, we can think of arguments and parameters as kind of the same thing. Yeah, parameters are what we pass into the function to get things. This is not a very extensive explanation of functions. Boy, we're getting a lot out of this. Okay, we're going to talk about it then. So here is the sum function that is already written for us. I used it earlier because I was cheating. And within the sum function, we pass into a list of numbers, right? And not only can we pass into a list of numbers, we can also just like pass into it different numbers itself. So what does this do? The sum function basically is there's something behind in Python's code where it defines, okay, whenever you pass in a list into the sum function, we want you to add up all the numbers in the list together, right? X is equal to sum and we print X, right? Sum list, it'll give you the sum of all the numbers in the list, right? And if we want to add more numbers to add, turn the sum. Oh, okay, I guess that's not how sum works. Anyway, you'll notice that like I started typing and then Google Colab started just like giving me information about it. That's a really nice part of Colab. It'll give you function information, yeah, on the fly. So yeah, this will just give you the sum. That's what Python has defined sum to do. It's been a weird explanation of functions. Does anyone have any questions?
Yeah. So are what were the methods that we've already discussed? Are those functions?
Okay. So this is that's a really good question in that it like kind of delves into the heart of something called object-oriented programming, which is definitely not within the scope of what we're talking about. But I'm more than happy to talk about it, which is that like whenever we have methods, we associate methods with objects, right? This list one, is an object, right? And if there are specific methods that are associated with the objects, right? Like they have gone in and they said, okay, list has to have these certain properties. And with these properties, we need lists to be able to do these things. So we need the list to be able to append elements, and we need the list to be able to pop elements, and we need the list to be able to do this, that, and the other thing. That's methods. Methods are explicitly related to a particular object or a particular type. Functions, on the other hand, let's let's call a function func, right? Functions are not associated with a specific object or type. Granted, sometimes we're going to have to pass in specific objects or types into the function in order for the function to work, but there is no like association that says, okay, we have an object, it has to be able to perform this method. Does that make sense? Okay, cool. Methods and functions, pretty similar in that they both like take a thing and do a thing with it. They're both like processes. But yeah, methods are like explicitly associated with an object. And also in Python in specific, you'll notice the difference because a method uses dot notation and a function will use this notation. Cool. Let's look at another example of a function. Power, great, pretty explanatory. It takes the base, raises it to an exponent. Let's say you forgot like which order it's supposed to be. Again, Colab, it'll tell you how x, y, z equivalent to x to the y power. And you can pass in z sometimes if you want to get a mod. So yeah, let's try passing in power 2, 3, this should be 8, right? 2 to the third is 8. Yeah, that's pretty explanatory. So the idea with functions, you pass in things, it'll give you out things. I mean, think of a function in math, right? You have an input, you have an output. You give 2 and 3 as an input, they'll give you 8 as an output.
Wait, sorry. So they're just like a set amount, like their functions are just commands. They're just a set like group of things you can put in, like power or sum or whatever.
Yeah. So, okay, good question. There are a lot of like set commands that set functions that Python has already told us that Python has already defined for us, right? Sum, pow, what else? Min. We have max. We have a bunch. Doesn't matter. The real hang up, no, not hang up. The real trick here, and we don't really go into it because we don't end up having to do it for a lot of data science stuff because data science has been around for a little bit and like people have already done it for us. The trick is that we can write our own functions. And like we won't get like super into it here, but like basically it kind of looks like this, right? And then funct, print arg, print I'm a function, and then if we say, oh my lord, right? It'll basically what it says like, okay, I see that you're calling a function that you wrote. I'm going to say that arg is equal to the string a. I'm going to print arg, but arg is a, so I'm printing a, and then I'm going to finish up the function, just do everything that you told me to do, print I'm a function. That's a real trick here. We don't end up actually having the need to define any functions for the sake of data science, because there's been a lot of groundwork already laid for us. But if you want to define functions, this is what it looks like.
But like, so we could make our own function that did like the while loop that we already created, like, and pass it, like, and say, oh, this function now just adds lists if we pass it a list.
Yeah, like if we want to remember okay. If we want to write our own like version of the summation, right, as we did above, we could do exactly that for item in L, and we're pretending L is some list that they gave us of numbers. For item in L, we actually have to start with 0. For item in L, total plus equals item, and then we could print total. Right, and now if we do summation 1, 2, 3, 6, right? That's the idea with functions. Now instead of having to type this every time, all we need to do is type this. Does that make sense? One last little trick about functions. If instead of like printing it out, like if we do this, single summation, print x. Yeah, like x is actually none. This is what I was talking about earlier about like you're printing a process, but you're not actually printing a thing. This is what I was talking about earlier. Like d.items is a method, and in this instance, we could think of it as a function. It returns a thing, but like printing it is a function. And so when we try to print the print function, when we try to print a procedure, it's like not a thing, right? We can only print it if it is a thing. And by thing, I mean not a function and not a callable and not a procedure. Could you print a callable? Kind of. It's not going to give you what you think it's going to be, though. So you got to be careful about that. So what if we do want to say that x is actually equal to a number? Then we have to use the keyword return total, right? What does this mean now? X is equal to 6. This means we could, x is like actually a number, right? Type x. X is actually a number. If we didn't say that and we just left it at print total, x is a nothing, right? Weird thing here is that like, yeah, if you set x is equal to the name of the function, then x is like a function type, which is to say it is a process. But once you call it, and you call it by adding the parentheses around it, it does, unless you use return, then it's not like actually a thing. It's a thing once you've returned the value at the end of the function. Then after you call it, which is to say you add the parentheses and the arguments after it, then x is equal to whatever return is. We're returning total, x is equal to total. Total is equal to sum is 6, x is equal to 6, and x is like actually an integer. Cool? Okay, we are swiftly running out of time, and we still have one more thing to talk about. And I haven't motivated dictionaries yet. Okay, so much stuff. Yeah, so what do you think happens when you don't pass the right amount of parameters into a function? I'll answer this question for you. It crashes. It doesn't work. Let me give you an example. Let's actually just literally use this. Summation 1, 2, 3. We've passed in one parameter. Let's pass in another parameter, 12. Uh-oh, it doesn't know what to do with 12 anymore. So that's a lesson for you guys. Pass in the right amount of parameters. That's why Google Colab will give you a tooltip, so you can actually pass in the right amount of parameters. Great. Okay, modules and packages. Okay, so the idea here is that like, okay, we could keep writing functions, and we could keep writing like a million different things over and over again, and like every single programmer on Earth can write their own versions of things. But wouldn't it be way easier if we could like work with code that was already written, that other people had already wrote, and then we could take it and like work on it and like build off of it instead of having to all write individually different things? Like that's just a bit of a hassle. So that's the idea behind modules. Modules are full Python programs that we can take that other people have already written, and they have functions that we could take and we can use. An example of this is the default math module. This is like a module that comes packed in with Python, and it comes in with like a lot of math functionality. Here's an example. We import the module math, and then whenever we want to call a function from math, we have to use math, the name of the module, dot, and then the name of the function. All right, so math.ceil 3.2. Ceil is the ceiling function. It takes some decimal and it rounds us up always to the nearest integer. Okay. Yeah. Here's some quick. We'll look at it in the code, but basically, if we want to figure out what functions are in a package, we call dir. If we want some help on what a function is, we call help. That's a nice one to add. Packages. Sometimes packages are really big, so there are like sub packages or folders to store like more packages within them. It's basically like a way for us to organize our code and like the code of different packages so that we can access it. Here's an example, right? What are we talking about? So within the package, like pandas is a big package that we're going to be working with, right? So within pandas, there's the module called testing. And then within the module testing, there is the function assert frame equal. This is just a way to keep organized, right? Testing is a module that is within pandas, and function is a function within module. Does this make sense so far? Okay. In the last 2 minutes, I feel like modules are more so of like modules are more so like an organizational thing. It's basically letting us reuse code that other people have already written. Gives us some time. So we'll run through this. Here's math. Math is a library. Math.seal. We're rounding up. That's 4. That's fine. That's what seal does. If we want to look up every single function that's within the math package, here it is. That's a lot of functions. And if we want help with it, great. And yeah, this won't work. But basically, pandas, which is a package that we're going to end up working with, has a module named testing, and then within it, we looked at this. Great. Okay. This is a lot. 1 minute takeaway. Now we know some things about Python. And now that we know some things about Python, we're going to look at pandas. Hey, pandas. We're going to look at pandas next week, which is like a Python package to organize and manipulate data. Whoa. Okay. I'm going to stay here and I'm going to talk about dictionaries and for loops and while loops for a little bit. No, none of you are required to stay. But if you want to join me on this weird little adventure with dictionaries and more stuff, I will be here. But if not, that's cool. Thank you for coming. I will upload these slides to the folder as soon as I'm done streaming. If you have any questions, as usual, go into the Slack. Let me know. Let Trey know. Let anyone know. We're here.
Yeah,
Okay.
I have to run, but thank you.
Yes, of course. Yep. All right. Oh boy, I don't envy lectures. This is a lot. Okay, let's talk about dictionaries and methods and loops. Okay, D is equal to, let's make some example. A1, B2, C3, whatever. Okay. Now let's say we want to add every value in D, right? I.e., we want to find 1 plus 2 plus 3. Now, if D was just equal to this, we already know how to do that. But D is not that. D is a dictionary, so it's a little more complicated than that. What do we do?
Don't we have to call it by the keys? That's
almost. You're on the right track though. Let's remember that d.keys gives us ABC. But we don't want the keys. We actually want the values, right? D.values. Do this. Okay, great. And remember how I said, like, for all intents and purposes, this is a list. So we could do the same thing as we did before. For, we have to say total, for, and I'm going to use just I in this case, in d.values, total plus equals I. And now we can print total. And okay, so that's the point of having values. Same idea goes for keys. What if we want to print out? We want to print out A, B, C, right? Instead of d.values, we now have d.keys, and we're not going to start with total. We're going to start total equal to the empty string ABC. Great. Now, okay. I know I just did this. I know I just did this, but don't do this. And here's why. It keeps coming back down to this. at least for this example where I got ABC, remember when I said that there is no inherent order to the key value pairs in a dictionary? This is what I mean. We can't rely on the fact that, like, I know it's weird because in my, like, I get how you might feel. Like in my computer science education, they've always been like, don't depend on the order of key value pairs. Don't depend on the order of key value pairs. But every time you look at a situation where you could depend on the value of key value pairs, it seems to be there for you and it seems to work. Don't do it. It doesn't semantically make sense. I mean, like, if it works for you, then it works for you. Like, don't listen to me. Like, what do I know? But semantically, depending on the order of the key value pairs in a dictionary does not make semantic sense. Or it doesn't make sense within the architecture of a computer. And you're like not guaranteed it. So yeah. That's the idea. For total is equal to, for the example where this is the case, it doesn't matter so much because like it doesn't matter what order you sum the values, you're still going to be that. Yeah. Okay. What else? What else did I want to talk about?
So I guess what you're saying is that if we'd called that code, you're saying that there are instances where it would be A, C, B.
Yeah.
Okay.
Yeah. The order is not inherent to the dictionary. So lastly, I want to look at, what if I wanted to print out like, is that a good example? Let's say we want to print out A1, B2, C3 in no particular order. Yeah. And by no particular order, I mean like I don't care if it's A1 first or B2 second or C3 third, but it's going to end up being that way. Do you have any ideas?
We could use items.
Great. Okay, so for I in items, let's just see what happens. Oh no. Print I, what does that give us? Okay, we're part way there. Now we want to print it. Print, I mean, that's what we had. But we actually want to print A1. So, I mean, these are just tuples, right? So I is some tuple. And if we want to access A, we get that. And if we want to access 1, we get this. Except this isn't going to work because this is the same thing as saying like A plus 1. What is A plus 1? That's like not a thing, right? You can't add letters to numbers. But we can add strings to each other. So we could turn this number into a string. And now this is going to be A plus 1, which is equal to A1, right? We can add strings together. On that. Right. And now we have that. And I'm being a real stickler here. I want to add the commas and I want to make them all on the same line. So commas, and then we can pass this into print. Yeah, the print is just another function, right? We've talked about functions now. Print is a function. We have optional parameters that we could pass into print. These optional parameters, we have to give the name of the parameter. In this instance, sep is the name of the parameter. And sep, we want to set to the empty string. Normally, sep is what what comes immediately after the print statement. Normally, sep is like a new line, right? If we don't say what sep is, then the way that print separates one print statement from the next print statement is just a new line, right? But we don't want the separator to be a new line. Actually, we want the separator to be this comma space. That's not quite it. Oh, sorry. I mixed up sep and end. Whoops. So take everything that I said about sep and apply it to end. Yeah. Okay, does that make sense? Right. So that's the idea behind dictionary values and items and and keys. That's how we make dictionaries work with for loops. Yeah. Okay. I have run out of things to talk about. Python is intricate. Even though it is beginner friendly, don't get me wrong. But if you dig under the hood, there is a lot, as with any other programming language. Very technical stuff. But yeah.
And I just had one question. Right at the end, we were talking about modules and packages.
Yeah.
And then I think a couple times really fast you said something about libraries.
Libraries is another way to say the phrase packages. Okay. So I should have specified. Yeah.
I was thinking there's a further, but packages are library. Okay. There's not a higher level called library and then packages and then modules.
Honestly, if I'm being fully honest, I have used the phrases library, package, and module interchangeably since as long as I can remember, and no one has corrected me. I mean, either no one's corrected me, or just everyone else thinks the same. Regardless, I'm probably gonna keep doing it.
But there's not a third level.
As far as I understand, no.
The one level, the two level, and then the function within. Okay.
Yeah. And this isn't this is kind of a weird detail, but not only can you call functions from modules and packages, you could also call objects. No, you know what? That's there. Rabbit hole, right? Rabbit hole. There's so much you can go down. Objects are functions, but more. Functions, but more. Yep. Okay, we won't go there. But yeah, you could basically access any portion of someone's code from a module, so long as it's something that they've defined. Yeah. Okay. Anything else?
No, I think I'm good.
All right. Well, I want to thank you for sticking with me here, and I will see you hopefully on Thursday.
Yeah. Hey, I really appreciate it. Have a good night.
Of course. Yeah. Take care.